Hi, my name is Junho Kim from Seoul National University. Today I'll present our paper titled Learning 3D Scene Analogies with Neuro-Contextual Scene Maps. In our work, we propose a new task of finding 3D scene analogies. Given two scenes containing regions with similar scene contexts, 3D scene analogies are defined as dense, smooth mappings from R3 to R3 between the regions. The ultimate goal of scene analogies is to have machines understand the often complex and high-dimensional scene context information. Such information is very hard to explicitly specify using language, let alone via any other symbolic system. We thus turn our attention to teaching machines the capacity of analogical reasoning, similar to how humans understand scene contexts. In a practical perspective, scene analogies can be useful for applications in various tasks requiring fine-grained 3D transfer. First, one can transfer trajectories of a humanoid agent while preserving the contextual information, which will aid in imitation learning or robotics applications. Second, one can transfer object placements between scenes, which enables AR/VR users in different spaces to virtually interact with each other. Now I will briefly describe our solution to the 3D scene analogies problem. Our pipeline takes a target scene along with a region of interest that specifies the region to match, and a reference scene to match against. Given these pairs, our method first extracts a descriptor field densely defined over the 3D space and finds a mapping that best aligns the two descriptor fields. The output is a mapping that transfers points from the region of interest to a corresponding region in the reference scene. Now let's dive into the details. First, descriptor fields are defined for arbitrary points in 3D space and summarize the nearby contextual information. As shown in the figure, given an input 3D model represented as sparse keypoints, the descriptor field at point Q is defined as the aggregation of distances and semantic information of points within a radius R. The input information is passed through a transformer to output the descriptor field features. To train descriptor fields, we apply contrastive learning. We use existing large 3D scene databases and create positive scene pairs via object swapping and negative scene pairs via adding pose noise to objects. Given the scene triplets, descriptor fields are trained through a standard contrastive learning process. Namely, we sample points near each object and enforce descriptor fields of positive pairs to be close while those of negative pairs to be far. Given the descriptor fields, we estimate scene maps through a coarse-to-fine process of first estimating affine maps and finding local displacements. Instead of finding point-wise matches, our approach finds the optimal mapping directly, which improves robustness to domain shifts and outliers. To elaborate, we align descriptor field values of points near the region of interest in the target scene and the warped points in the reference scene. As descriptor field values are standard neural networks, the cost function is differentiable and thus is optimized using gradient-based solvers. Now I will share some qualitative results of our method, first on synthetic scenes. Given these indoor scene pairs, our method can find good mappings that can make detail-preserving maps for both open spaces and points near the object surface. Our method can also handle noisy real-world scans. Similar to the synthetic case, our method can handle both open space and near-surface points. Further, our method can also handle sim-to-real cases, matching regions between synthetic and noisy 3D scans. These results can have applications in sim-to-real transfer for policy learning and robotics. In conclusion, we propose a new task of 3D scene analogies. Our solution, neural contextual scene maps, enable dense, context-preserving mappings between two scenes. With minimal changes in formulation, our method is applicable for synthetic, real, and sim-to-real scenarios. Thanks for listening.